So now we're going to prove Chigger's inequality and state it, right? So let's put the objects, right? So we have a graph, Laplacian of a graph, normalized Laplacian, as we saw. The Chigger cut of a cut is equal to the cut of that set over the minimum, over the volumes of the set and the set complement. Right? And now the Chigger number is just the minimum over these. We saw already the easy side of Chigger's inequality. Now I'm going to state the full Chigger's inequality. So theorem. This is Chigger's inequality. In these definitions above, we have the following. Right, so it says that we had already, right, this is the easy side of it and the hard side. Right, this is the easy and the hard side. Right, we had seen already the easy side, right? This was what we wanted to find, like good cuts of a graph. And this was what the spectral relaxation gave. And what this is saying is the spectral relaxation is not so different, right? At least the real cut is sandwiched between these two things, right? Between eigenvalue and the square root of eigenvalue. But actually we have something else, right? Remember what was the strategy of spectral clustering? Right, just to put the things back in the board. Right, the strategy of spectral clustering is to compute right? Phi 2. Right, phi 2 is obtained by taking the second eigenvector of LG and then multiplying by d half. Right, you computed phi 2. Right, was sort of the surrogate to the y that we saw in the cut, and then you thresholded it. Right, so you picked as tau as just being all values of tau, all indices I such that phi 2 I was bigger than this threshold tau. So the lemma we're going to prove today is the following. And this is the guarantee for performance of spectral clustering. It's going to say that there exists a threshold tau such that HS tau is going to be smaller or equal than square root 2 lambda. Right, and in particular, because we know, right, we know from the easy side of Chigger inequality, we also get that this is smaller or equal than 4 of the Chigger copy, or the Chigger number of the graph. Okay, so let's try to think about what this is saying. This is saying that if I do this strategy of computing phi 2, right? Remember, I take v2 and then I hit it with the d half, and now what we're seeing is that, right? What we're seeing is that by doing that strategy and picking the best possible thresholding, which we can, because there are not that many thresholdings that we can pick, right? There's of course many real numbers, but if we think of all the n numbers all done in in a line, there's just n different thresholds or n minus 1 different thresholds, right? And so we have to just try all n minus 1 different ones, and then we get some threshold. And now right, and now what this argues is that if we pick the best of the thresholds, then the best threshold will have a cut in the Chigger sense that is at least as good as square root of 4 of the best one. Right, so this is giving us some sense of guarantee that spectral clustering will not go completely crazy. The cut that we compute is that the worst possible it could be is square root of the optimal one calculated in this way. Right, and so what we're going to prove is this inequality, this lemma. And this, of course, immediately implies Chigger's inequality, right? Because for sure, this cut won't be as good as the best one, right? So the best possible cut is for sure smaller or equal than this one, and so it's smaller or equal than that. And so immediately this lemma will imply Cheeger's inequality. All right, so Cheeger's inequality was first described by Jeff Cheeger in 1970. Jeff Cheeger was interested in understanding this not for graphs but for manifolds, because a small cut is a bottleneck in a manifold, and think like a dumbbell, like maybe a manifold looking like this, right? This is like a bottleneck in the manifold, right? And so this should be able to be visible through the Cheeger cut, and the question was, can this be read off the Laplacian of the manifold? Right, and so this is what the Cheeger is a differential geometer, and so he was interested in these kinds of things, and as this was sort of not rediscovered, but more adapted to graphs than in graphs, which is a different type of, it's a different proof and so on, by Nogalon and then Millman maybe mid-80s. Okay, so the goal is we're going to prove this inequality, and this is quite a slick type argument. It's not a very simple proof, and it has really, really slick arguments, and so this is what we're going to do today. Right, we're going to do the proof of the lemma, and then immediately we get the theorem and we get Cheeger's inequality. We're not only going to prove Cheeger's inequality, but we prove a guarantee for spectral clustering. Right, so we're going to prove of the lemma. Okay, so we're going to prove something, right? We're going to prove something a little different, right? So there's many different proofs of this. There's a paper by Fenchung that has, Fenchung has a paper maybe from 2010 that has, I think, even 4 different proofs. I think it's called 4 different proofs of the Cheeger's inequality. This particular one is I saw in a blog by Luca Trevisan a few years ago. So this is a very slick probabilistic argument. Okay, so we'll show the following. We'll show that given y in our n, satisfying right, this with the Rayleigh quotient of y, which I'm going to describe. This being smaller or equal than delta, and y transpose d1 being 0, right? I'm going to show that if we have that, then there is a rounding of it. Right, by rounding of it, I mean, right, to take an s tau given by the entries of y and v such that, say, yi is significantly more than tau. Okay. With such that, it satisfies this problem. So h of s tau is now smaller or equal than square root of 2 delta. Okay, now why will this imply what we want? Okay, realizing that this is maybe a little dirty, let me clean them again. Right, a rounding of it such that h of s tau is small or equal than square root of 2 delta. Right? Why will this imply what we want? Because there is y such that delta is lambda 2, right? Just take y equals phi 2. Right? Just take y equals phi 2. And if you take y equals phi 2, delta is exactly lambda 2 of the Laplacian. Right? It's not so easy to see. If you take y equals phi 2, you get, right, this is exactly what shows up here is exactly the eigenvalue and right, and this was the constraint that we had to be equals to 1. Right, because when you write v2 with respect to y, with respect to phi 2, the d minus 1 show up, d minus a half show up here, give exactly the Laplacian, this is exactly the normalization. Okay. Okay, so now the trick is to use the probabilistic method. So I'm going to take a threshold at random and prove by the probabilistic argument type trick that there must exist one. Maybe, in expectation there is one, therefore there must exist. In expectation it performs like that, therefore there must exist one. Right? So we'll see exactly how that will work. So the strategy will be to use the probabilistic method, right? So we will choose pick tau and random. Okay, so let's simplify things a little. So we start by assuming that the y's are open. Right, this will just make it easier to explain the proof. Of course, in general, that won't be the case, but we can always assume this because we can just change the labels. Right? There's nothing special about the label 1 for the node and 2 and so on. You just redo the labels to make it like this, just for it to be easier for me to describe the proof. Okay. So another fact that's important is that scaling. Right? If I take y and I take it multiply by some constant. Right, scaling of y does not change the really quotient, right? Because the scale will show up here and there. Right, so scaling does not change R. Now, because, right, another fact, okay, so assumption number 1, fact 1. Right, fact 2. Another fact is since I have the orthogonality condition here, right, which is also satisfied by fact 2. Right? Since y transpose v1 is 0, then doing the transformation like y adding a multiple of 1, right? So adding a multiple of 1 can only make Ry smaller. It only decreases Ry. Okay, why? Because, okay, let's look at Ry. If I add a multiple of 1, then for sure this is going to stay the same, right? Because a multiple of 1, when it's in the 1 is in the kernel of LG, so this will stay the same. Now let's see what happens to that. Right, so let's say that the numerator stays the same. However, if I look at what happens to the denominator, right, the cross terms are 0 exactly because of this condition. So I get y transpose dy, and then I get c squared 1 transpose d1, which is exactly the volume of the graph. Right? So even for C positive or negative, this is for sure big or equal than y transpose dy. Right? So the value of Ry can only decrease, right? It cannot get bigger. So this means that if we start with y, I can, right, if I start with y satisfying this, I can now scale as I want, and I can add or subtract multiples of 1, and it will still satisfy that, right? Because it doesn't, one of the operations doesn't change Ri, the other one just makes it smaller, so it will still satisfy. Okay, so we're going to construct x, right? So we're going to build x1 to xn, right, by scaling and like translating, so adding a multiple of 1. All right, we're going to build these x's to satisfy certain properties, right? And what I want is the following. I want x1 is smaller than xn, right? I mean, I'm just scaling and adding a multiple of 1, so for sure that will be the case. I'm going to center it in a way, right? So this is where the multiple, the multiple of 1 is going to help me. I'm going to have, let me use the next line. I'm going to have xn be 0. Right? And I'm going to pick m very specially. I'm going to pick m so that m is always in the one. I want M to always be in the set with the biggest volume, right? I'm always going to threshold from 1 to n, and I want M in the place where wherever M goes, this must be the place with the biggest threshold. So I want M such that volume of, if I pick all the numbers from 1, up to, okay, I guess I should write volume of the node from 1 to n minus 1, right? This is smaller or equal than the volume of the others, right? With n all the way up to n. But if I do it the other way, if I include m on the left, then I go bigger. So m is exactly the place at the middle of the volume. Okay, so think of m as in the middle in the volume sense. Right, middle, maybe I should write that even smaller. It's like in the middle in volume sense. Okay, now I'm going to ask something else. I'm going to normalize it, right? I take y, I move it with the multiples of 1 for it to be 0 here, and now I can add a multiple or subtract a multiple. I'm going to normalize it, and I'm going to normalize it so that x1 squared plus xn squared are equal to 1. Okay, and for sure, because I constructed it just by scaling and adding and subtracting multiples, I'm going to have the following. I'm going to have, with the same thing that was true before, is equal to 1. This is smaller equal than delta. Okay, so now I'm going to pick tau with a very particularly chosen distribution. Right? I'm going to pick tau at random. Okay, now we pick tau at random. With the following distribution, right? Tau will be between, right, of course, it doesn't make sense for it to be anywhere else, it will be between x1 and xn. Right? If I think of the x1, x2, and all the way to xn, I'm picking tau somewhere in the middle. Right? And now I'm picking it with a very particular distribution, so that for all a and b, the probability that tau is in the interval ab is equal to plus the norm of tau d. Okay, so this seems a very strange thing. Of course, for b, it's bigger or equal than a, bigger or equal than x1, smaller or equal than xn. Okay, now let's look at the probability. It's not so hard to now work out the integral, right? The probability exactly for a is in the same. It's not so hard to check that the probability for tau to be in a and b is given by the following. It's given by b squared minus a squared if a and b have the same sign. And it's given by b squared, a squared plus b squared if different sign. Okay. So in particular, because x1 and xn, they must have different sign, right? Because xn is at 0. So one of them, x1 is negative for sure, and xn is positive for sure. So the probability of tau being inside x1, xn is normalized the right way, right? This is 1, right? So at least that, that sanity check works. Okay, so let me erase this side. Okay, now, right, the slick part of the argument is picking this distribution. Now we have to prove that this is a distribution that we can say that an expectation or with high probability something like this, we actually get a tau that works. Right, so let's start by estimating the expected value of the cut of the set S that we get. Right, so what is this? This is equal to, we get expected value of, now I'm going to sum this in a different way. I'm going to sum this over all i's in the vertex, all j's in the vertex, right? And now I see it, right? I get the weight, and I get the indicator of ij being in the cut. S, right? And I now am summing I in S and J in S complement, and I in S complement J in S, so I need to take one out of this. Right? So every edge is being now shown up twice, right? And now this is just one if I and J are cut by this, and zero otherwise. Right? So now what does this mean? Right? I can move the expectation inside. The expectation of an indicator is just a probability. Right, it's one of the neat things with the probabilistic method. Here lies really the key step, which is linearity of expectation, which is that the expectation of something I'm counting, so I can write it as sums of indicator functions. I can move the expectation inside. By the time I go inside, they become probabilities, and I start looking at sums of probabilities, which is a lot simpler to study. Right? Even though these events are not necessarily independent or anything like this, you know, so it's not a priori obvious that the probability of the cutting of a certain size can be described easily in terms of the probabilities of each edge being cut, but the expectation, however, can. And if we argue that the expectation is bigger than something, then it must exist tau such that that is satisfied, right? So this is the key of the probabilistic method, is the fact that this is doable. So linearity of expectation is really the most important. Okay. All right, so let's go on. Now I get WJ probability of the following: S complement cuts the edge. Right. Now, of course, we know what that is, right? When is it that S and X complement cut the edge ij? It cuts the edge ij exactly when tau is between xi and xj. Right? So we know that the probability, right? This probability, right? Right, is equal to what? We know that it is equal to xi minus xj squared. Xi squared minus xj squared, right? Exactly this, if same side. And xi squared plus xj squared, if different side. Now the nice thing is that even though that looks, you know, this is exactly just copying from there, right? This cuts if the threshold tau is between xi and xj, right? But now both of these expressions get easily bounded, right? Regardless if they have the same sign or not, they get very nicely bounded by xi minus xj. Right? If they have the same sign, then we're getting exactly this expression. If they have a different sign, then this is just summing them, and so we just get the sum squared, which is bigger than the square of the sums. So we're just getting the square of the sums, which is bigger than the sum of the squares. Right? If they have right of the absolute values. Okay, so this means, what does this give? All right, so let's erase this part now. Okay, so as you can see, there's a bunch of slick tricks one after the other. Let's see, so what we get is expected value of the cut S, right? What is it equal to? Or smaller equal to, now that I'm bounding it, smaller equal to 1/2 times the sum over I and j of wij times now this expression. Let me go to the next line, or erase this part so that I'm not making a mess. So far, so good. Now we do Cauchy-Schwarz. This is Cauchy-Schwarz. Right, what does Cauchy-Schwarz give us? Right, I'm doing Cauchy-Schwarz on this, and the square root of that, and this, and the square root of that. I get square root of sum ij of wij. Right, you're seeing a Laplacian already showing up here. Right, so okay, so let's now try to understand what this expression is. Right. This here, or let's say this here inside, is exactly square root of twice, right? Because now I'm not saying I smaller than j, I'm summing over everything. Twice x transpose Laplacian g of x. Right? This is equal. Right? But we know by the definition of right, so square root, right, of 2. But now we know, because x satisfies that inequality on the Rayleigh quotient, that this needs to be smaller than delta times x transpose dx. Right, so we have that. Okay. So now let's see what else we can say. So what about this expression here? We get square root of, and now what we have for every I, I'm summing, right, the sum of, well, there's squares. There's a square missing here, right, of course, because Cauchy will give me a square there. So now, this, I'm going to bound. Right? I'm going to bound this. This is, of course, xi squared plus 2xij plus xj squared. But I'm just going to bound it by twice xi squared plus xj squared, right? So this is smaller or equal than 1 over ij of wij, right? And then twice xi squared plus twice xj squared. Right? Because I get xi squared, xj squared, and then 2xij, but 2xij is smaller than xi squared plus xj squared, so I'm just putting the 2 here. Right, but now this is easy to see what this is, right? Because what is this? This is just equal to, go over here instead, right? We just get 2, and then we're just summing. Right, we're just summing I, we're just summing over all I, the wij xi squared, so this is just xi squared, it's just the sum over I of xi squared degrees of I, right? Plus is the exact same thing over the j. So all this is, right, these two terms are exactly the same, and all they are is just x transpose dx, right? So this is exactly equal to square root of 4x transpose dx. Okay, now let's try to put everything together. Okay, so what we have here, we have that the expected value, the cut of S, right, the threshold tau. Right, and I'll put all this in the lecture notes, of course. So the threshold is smaller or equal than, right? So let's try to put everything together and not make a mistake. We have 1/2 square root of 2 delta x transpose dx times square root of 4 times x transpose dx. So what is this? This is, okay, let's do it. So small or equal, we get the 2, cancels with this 2. So we get square root 2 delta, right? This house cancels with that 4. We get square root 2 delta times x transpose dx. Right, but now we have, okay, so we already have, then we know that the cut in expected value is smaller than equal to this, so we're getting somewhere. But now we have to also describe the expected value of the minimum of the volumes, right? In order to talk about trigger cuts, we still need to do this. So let's do that. So I take the expected value of the minimum. Okay, so now what is this? Well, this is the sum over all the nodes, right? And the node contributes to the volume, the degree. And he contributes if and only if it is in the smallest cluster, right? So the probability that I is in smallest cluster. Right? This is exactly linearity of expectation again, right? Here, this is the expected value of the sum of degree of the indicator being the smallest cluster, but this is the same thing as just taking, right? As just taking, this is the same thing, right? Because they're move the expectation inside, expectation of the indicator function is exactly the same thing as the probability, right? And so this is how we get this. Okay, so if you remember what were the probabilities, right? The probability of things, two things being in the same cluster was the probability of two things being in the same cluster, right? We saw was this different expression with different signs. But now, if we have to break, if the volumes are the same, okay, let's break ties. If the volumes are the same, we say that the vertex M, remember the one at 0, is always in the largest cluster. So something is in the smallest cluster if and only if it has the threshold separates it from xm. But remember, xm was 0, right? So since xm was 0, the expressions are the same, right? We get that the probability that xi is in the vertex different, is in the cluster different than xm is just xi squared, right? Because it was xi squared plus xm squared, say, in one of the cases, and xm is 0. Right? And in the other case, it would be exactly the same thing. So this means that this probability, right? This probability, the probability that I is in the smallest cluster, I should say in terms of volume, right, is exactly the same as the probability of xi, of, I should say, of I and m being in different clusters. And since xm is 0, the probability of this is just exactly xm squared. Okay, so because the probability of this is exactly xi squared, then this is actually very easy to write, right? I just get sum of I degree of I xi squared. This means that this whole sum, right, is exactly x transpose dx. Right, so what do I have? I have that the expected value of the minimum of the volume, this volume mass complement, is exactly equal to x transpose dx. Okay, so what do we have now? Let's now write everything that we have to finish the proof. We're almost there. Okay, so we have that the expected value of the cut S is smaller or equal than to delta, and now we also have that. We also have that the expected. This we actually have equality. We have that the expected value of min there's an right, what we want to show now is that there exists an S for which this over this is smaller or equal than 2 delta. Right? It seems like we're almost there because notice what we have. We have that the expected value of the cut of S over the expected value of the min between the volumes smaller or equal than 2 delta. Okay, so the probabilistic argument usually goes, if I can show that the expected value of something is smaller than something else, it must be that there exists an instance that is itself smaller. But notice that it's not quite the same, it's not quite what we have here, because we do not have, right, it's different, or I should say, this is not equivalent to saying that the expected value of the quotient of the same thing is smaller or equal than square root of 2 delta, right? Because just I cannot move the expected values outside of the fraction, right? So I'm not quite yet done, right? But how can we now finish? Well, we now can use linearity of expectation again, right? We just have to move this one over here, right? Because we now have the expected value of the cut of S is smaller or equal than square root of 2 delta times the expected value of this min. Right? Now I can move it the other way. Now I get that the expected value, right? And expected value is now linear, so this I can do. And the cut of S minus square root of 2 delta times the minimum of the volumes is smaller or equal than 0. Now the probabilistic method works because now I have a random variable whose expectation is negative or non-negative, non-positive. It must be that there exists a threshold such that S satisfies exactly that this is non-negative, because if for all S's this was positive, then the expectation would also be positive, right? So it must be that there is a sense such that the cut of S minus this is non-negative, meaning that, maybe I'll write this all the way, right? 2 delta minimum volume of S complement, and now this is smaller or equal than 0, but if this exists, right, I just have to redo the thing. The same thing, I have to move this to the side and divide, and I get that there exists a threshold such that the S satisfies that the cut at H of S, which is the cut of S over the minimum of the volumes, right? it's smaller or equal than square root 2 of delta. And now because delta was, I think I could take delta to be the eigenvalue, the second eigenvalue of a Gaussian, and I'm done. Right? Because remember that this delta for phi 2 was exactly lambda 2 of the normalized Gaussian. So I'll put all these in the lecture notes, this proof. There's a lot of, you should try to go through it again. There's a lot of slick tricks, especially with the picking of the probabilities and cool uses of Cauchy-Schwarz and so on. There's many other proofs of this, some of which are a bit more transparent. Like they actually work by rounding the vector and studying the rounding. They're not as quick to present. They're a bit more complicated, but they're more transparent. I quite like this one because it shows the power of the linearity of expectation as it showed up here at some point. It has this cool thing that you're not quite done when you think you're done. And it's just a really slick argument of the probabilistic method, which is usually actually a lot for rounding. Lots of the roundings that we'll see for algorithms later on, like for max and so on, will actually themselves be probabilistic, right? Here, the rounding, since there's only n nodes and you only can cut them in the line, there's only n or n minus 1 different cuttings. So you can just try all of them. So how to pick the best rounding is not really important. You just try all of them. But as you're going to see now, the problems are going to be exponentially many different ways of rounding. And so picking which one will actually be a challenge, and this will be done randomly. Right? And so this finishes sort of the chapter or the series of lectures in graphs, and we're going to move, or in spectral graph theory, we're going to move to diffusion maps and then linear embeddings, where we're going to do exactly the idea of how do we take a graph or a manifold or something and we embed it in Euclidean space. Right? How do we take a graph and how do we visualize it in Euclidean space? Or if we have a curved manifold, how do we uncurve it? How do we make a graph first out of it and then we embed it in Euclidean space? And this will sort of bring us to a different type of techniques, not super different from this, but more in the style of manifold learning style. Okay. Thank you.